Today, we're going to finish our quick review of interphase mass transfer. And, we'll also do, or at least get started on a problem example. So in particular, what I want to cover today is gas film versus liquid film controlling resistances. And then compare gas absorption versus liquid stripping. And in that context, we'll look at continuous well-mix processes for those processes. And then we'll get started on and hopefully finish problem 1.9 revised, which is on Canvas under a new module called in-class problems. And so you can pick it up there. It's also in the course packet. As far as for announcements, I put on the Canvas announcements, the announcements for quiz 1. All right, and it'll be available on Friday, October 2nd, and it'll be on topic 1.1, and the various details associated with quiz 1 are provided on Canvas. So you want to see the Canvas announcements for details. All right. I also want to talk real briefly about what's going to happen tomorrow. Tomorrow we're going to have a situation where we're going to have about half the class with an in-class experience and half the class still remote. So there's going to be 4 recitation sections tomorrow. There's no grading associated with them, all right? But especially for the section at 10 a.m., section 11, we'll ask you to stick to that because that's an in-class one and it's close to capacity in Gilfillan Hall. And for those of you that will meet in person, you'll meet with me. And for those sections where you're meeting remotely, you'll meet with Dr. Lambert. And the focus of those sessions will be mainly to do some problem solving that will be instructor led, and then to answer any questions that you might have with the homework. And so that's what's going to be happening tomorrow. So with that, let's get back to our lecture for today. All right, what I'm going to try here is to put 2 versions of the course packet side by side so that I don't have to go back and forth between comparators for one page versus the other. So where we left off last time was this description of an overall mass transfer coefficient. And just to review just a tiny bit from the end of class yesterday, we first looked at the definition of a gas film and liquid film, because remember, in gas absorption, the same flux goes through the gas film and then through the liquid film, but they have different driving forces and different units associated with their mass transfer coefficient. So for example, in this diagram here, if you are looking at gas absorption, then the driving force will be YA minus YAI. And the film mass coefficient will be KY. And then on the liquid side, the driving force will pick up from the liquid side and go from XAI to XA. And in that case, the driving force will be defined by XA minus XAI, and that driving force multiplied by the mass transfer coefficient K sub little x gives you the same flux. And remember, at the gas-liquid interface, there's this case where we have local equilibrium, where there is thermodynamic partitioning between the solute distributed between the gas and the liquid phase, but only at that point within the process. Now, what we further did was we defined an overall mass transfer coefficient. So if you look to the diagram on the right here, notice you have these equilibrium compositions, XAI and YAI, but they only exist on the equilibrium line because they're in local equilibrium. So that's given by this point right here. Let's see here. I'm just gonna looks like I can't do that. So anyway, YA and XA are going to be defined by the operating point given as XA comma YA. And it will be back to this, just one moment. Oh, let's see. Well, we'll just stick with this for now. Just one second, I've got to call the file back up. All right, there we go. So again, this point right here, this is this equilibrium composition, and I want to emphasize it's the only thing on the equilibrium line. Although the equilibrium data may show PaCal, that's assuming that the whole process is at equilibrium, which is not the case, because in this case here, it defines what's called the operating point, all right, which is not at equilibrium. And it's a locus that describes the composition in the bulk gas and in the bulk liquid. And so when we move over to mole fractions, then we see these equivalent expressions in mole fraction coordinates. Now, another thing that we need to look at is this idea of the driving forces plotted on this diagram. And just trying to draw in here. What I'll do, I'll just draw it. I'm just going to draw it right on the diagram here. That's just going to be easiest for me. And we're going to use the mole fraction base coordinates. And if you look at this driving force here, this is going to be YA minus YAI. And then this driving force here, down here.
Dr. Rohr, we don't see what you're doing.
Can you see the dot cam?
No.
I can see.
Yeah, you got to pin the video.
Oh, okay.
It shows that I'm on the dot cam.
Thank you.
Yeah, a bunch of chats about that won't help unless you're talking to other people, because I won't be able to open the chat while I'm doing this. All right, can everybody see this? Like, am I waving my hand, yes or no?
Yes.
All right.
Doing it, you're good.
All right, so back to where we were. All right, so then this will be XA minus XAI. And the reason why I'm recapitulating this from yesterday is because I know where people get hung up, and it's always on this. It's not on the mechanics of using your calculator with these ideas. It's understanding what this stuff really means. So this is the driving force down here, all right, in the liquid phase. So we can just say liquid here and gas here. Now, we can define another driving force in consistent units that goes from YA to YA star. And we can do the same thing down here that goes all the way from XA star minus XA, because notice here XA star is bigger than XA, because we're moving from the gas to the liquid film and then from the liquid film into the bulk liquid. So what we defined at the end of class last time was that N sub A is going to equal to big KY, YA minus YA star. But the big KY is really the reciprocal sum of the gas film and of the liquid film, where the liquid film is moderated by the local equilibrium given right here by M prime. So if this is linear, then M prime is equal to M double prime, which is the slope over this range here, which is equal to M. But if they're nonlinear, then you have to account for this. Now, this is for the gas. It'll be called overall, because we're talking about going through both the gas film and the liquid film using YA star as that consistent units to define that K, capital K sub Y. And now for the liquid overall. You have the same thing, but now you're referencing that you have KX here and KY right here, and now that's going to be respect to M double prime right here. Now in reality, these M and M double prime, M prime and M double primes don't change a whole lot in numerical value. So this is mainly a theoretical significance, but nevertheless in the development, they are different. So this is essentially to where we got to the end of class on yesterday. And what I want to do is move on, and in this context of this discussion, all right, talk more about how we're going to analyze the limiting resistances in this process. So I'm going to go back to lecture notes packet. And the first thing that we'll do is that we'll define what relative resistances are. You can think of the relative resistance you can think of the relative resistance as reciprocal of the film and the overall driving forces. Because what will happen is that the small gas film coefficient will always be larger than the overall coefficient. So one way to look at how we define those resistances would be to just consider that this is just going to be all equal to big ky on little ky, and that's going to be less than or equal to 1. And then likewise, you've got the same thing with the liquid resistance. And so this is what I brought at the end of class on yesterday, is that the big ky is always going to be smaller than the little ky. And that needs to make sense to you, okay? Because when we look at the driving force here, okay, we see that the driving force, YA minus YA star, is larger than YA minus YAI. So then what will happen in this case is that if we go back to this diagram here, I'll have the diagram here and the explanations on the right. As the value for M gets small, if you just look at the value for M right here, which is reflective of Henry's law, as that value gets smaller, then what happens is that the contribution of this term gets smaller, but it's expressed as a reciprocal sum. And so what that ends up doing is it moves big ky to the value of little ky. And in so doing, it pushes this downward, all right? So that ultimately, YAI approaches YA star, and XAI minus XA approaches 0. And this is called a gas film controlling resistance. And so you can do the same thing with the liquid film, all right? If you have a situation right here where M or M double prime is very large, then what will happen is that this term here will then become small, and big kx will approximate little kx, and the driving force in the gas film will move to 0. And so this can also be moderated by the relative values associated with kx and ky, as you have a large slope, which would indicate a small ky, you move the driving force mainly into the gas phase. If you have a slope close to zero, which would indicate a small kx relative to ky, you make it liquid film controlling. So in both of these cases, what happens is that depending on the magnitude of the mass transfer coefficients in the film and the Henry's law constant, you can affect to have one resistance to be controlling. And that would be fortuitous to have in situations where you don't want to necessarily have to calculate the overall coefficient. If you know it's liquid phase or gas phase controlling up front, then only the gas film resistance is important or the liquid film resistance is important, and you only need the mass transfer coefficients associated with those, depending on the type of resistance that you have. So I'm going to do two things now. I'm just going to share a Excel sheet, and I'll post this little Excel sheet to Canvas. All right, and hopefully you can all see this this Excel sheet. And just one moment while I get all this Zoom stuff out of the way so I can actually use it. So what we have right here is the XY diagram, and then on the left and then on the right, we can see the actual driving forces in the gas film in light blue and the liquid film in purple. And so, for example, if we changed the mass transfer coefficient, we'd imagine that we would change the slope of this little red line here that connects the two, and then we can watch all the compositions change. So let's just see what happens. All right, if we make that kx a little bit bigger, let's double it. All right, now you notice here that the lines don't quite link up. This has an implicit solution in it. Now we have to go to solver. And we just solve it. And I messed up. So let's just down a little bit different. All right, let's try it again. There we go. So notice it all popped together. Okay, and then we get a different set of driving forces. So I made a small change there, but I'll post that and you can play with it. But you know, it's not user friendly. You have to read the directions in red to use it properly. And if you make a mistake to any of the cells, it doesn't snap back. None of the cells are locked, so that you play with it. So anyways, this kind of shows you what can happen when you change any of the film coefficients or the equilibrium constants. All of these things change. And this is going to be an important thing to think about, because when we get into processes that utilize gas absorption and liquid stripping in a packed tower, we're not going to have one operating point. We're going to have a series of operating points, and each one of those will have a different driving force associated with them, and we'll have to figure out some way to integrate those driving forces over the device. So that's just a little heads up what's happening in the future. What I want to do now is just contrast between gas absorption and liquid stripping. let's see here. Back to lecture notes. Now we're going to still be in mole fraction coordinates here. So we've talked to death the gas absorption part. What I want you to do is just to look at gas absorption relative to liquid stripping. In liquid stripping, we have the situation where the source of mass transfer is the liquid and the sink is the gas film. So we have to be looking at this process here to reference liquid stripping. So just taking it right from where my hand is, here's XA and YA. But now XA is going to be greater than XAI. And because of that, the operating point for liquid stripping always has to be below the equilibrium line, because if you look at it from this perspective here, XA is always got to be greater than XAI. And if you can remember that, all right, by just looking at this diagram and then look at the XY plot, you'll always remember, all right, that the operating line has to be below the equilibrium line. And then beyond that, everything is described as before. So the good news is that whether we're working with gas absorption or liquid stripping, we can use the same set of relationships by convention, but it's not required. If we're working in gas absorption processes, we usually base all the calculations on the gas phase. Whereas if we're in liquid stripping processes, we base all the calculations on the liquid phase. But we definitely are not required to do that. It's just by convention. And then I won't go into the details here, but you can also define a consistent set of overall coefficients for liquid stripping. And they're the same, but the point of context is that if you have a non-equilibrium curve, your M prime and your M double prime are going to be defined just a little bit differently based on just looking at the plot here. So just looking at this plot here, the M prime and the M double prime are going to be defined a little bit differently, okay? And they're given here for gas absorption versus liquid stripping. So I won't go into detail there, but just to know that you have that situation. Now, the last little piece I want to talk about is interconversion between mass transfer coefficients. Just as we had interconversion between values of the equilibrium constant, we also have different ways that we can describe the gas and liquid film. So if we go back to this here, this is page 11. And then just look what we have here on the screen. All right. Then if we look at, for example, N sub A defined as partial pressure versus N sub A defined as mole fraction, and look at these two right here. All right, since we know that PA is going to equal to YA multiplied by P, then what happens is that when you interconvert those, you get little kg is equal to little k y divided by P. Now keep in mind, this also holds for the film, but it also holds for the big one. I have a little thing here to indicate that that's the film. And it also holds for the overall. It seems obvious, but a lot of times people miss that. But you can do the same thing. So I'll let you work on how those are derived in your own on your own time, but the concept of that is given here. This part here, unimolecular diffusion versus equimolar counter diffusion based mass transfer coefficients. We're going to wait until topic 2 to talk about that, because this enables us some convenience when we're dealing with mass transfer processes and gas absorption towers. And we'll not talk about that right now, but basically there's an equivalency between mass transfer coefficients based on EMCD versus UMD, and they're basically a correction for the inert gas in the gas phase and the solvent composition in the liquid phase. Now, last thing I want to overview is how you can carry out this in a well mixed process. And I saved this for homework, and we'll do an example related to these processes tomorrow. But basically, in a well mixed process, you've got continuous flow in and continuous flow out. And what we'll see when we analyze unit operations in mass transfer processes is that we'll base the material balance from 2 perspectives. In the first perspective, we'll do a terminal stream material balance with respect to all the streams, just like you did in 211. But then what we'll also do is a phase-specific material balance, and we'll use the flux to provide either the in term or the out term to that particular phase within the device to complete the material balance. So this will happen for a closed tank, but you can also have an open tank. And in this case here, your open tank is just open to the atmosphere. And then this is a particular case where you're either driving gas material in or stripping material out. And in the atmosphere, what we commonly do is assign a given fixed value of the solute in either the gas phase or the liquid phase. Like, for example, absorption might be you take carbon dioxide from the atmosphere and actually put it into liquid, which you can do. All right, works. All right. But then the carbon dioxide in the atmosphere isn't going to change a whole lot just because you put your little tank here. Okay, likewise, you could have a contaminant in the liquid phase here. And if you just put it here and expose it to the atmosphere, if it has a Henry's law constant with it, it could just go out into the atmosphere. Well, yeah, you're emitting something toxic into the atmosphere, but once it gets diluted in that atmosphere, it may not be in any measurable concentration. So often they just regulate these whole processes based on the flux that they emit, not the concentration near the device. So that's the quick review of interface mass transfer. I'd now like to see how far we can get on a problem example. And I'd like you to follow along. In Canvas, I gave you a picture of the plot. And also gave you the problem statement. And so I need for you to dig that up. I'll put it on the screen here, but it would be great if you could follow along too. Just one moment here while I dig up the problem. Okay, so here it is on the share, but I'll work on it off the document camera here. So we'll keep this handy because we're going to need a graph at some point. All right, but I'm going to just start without it. So there's some givens in the problem, And I'm not going to write all those down in the interest of time here so that we can get through this example. All right. But you'll be having to write down the givens, and I'll just be using the givens as I work through this. All right, so this is problem 1.9. It's revised. I made a little bit of change from what's in the course packet. And whenever I do that, I give you the changes. So you have that available to you. All right. In the part A, they're asking for the operating point. And in this process here, we have a mixture of ammonia and air, and it's in contact with water as a solvent. So this operating point here indicates these non-equilibrium compositions that we have both in the gas phase and the liquid phase. And then what we know is that PA, I'm sorry. We know that XA is equal to 0.0545. All right. And we also know that PA is equal to 0.2 atmospheres. And so if we go back here and just look at the plot, if I can get all this on here. Okay, then all we do is it just so happens that what we were given, we can just plot out directly. And so 0.0545 and 0.2 is going to be right about here. It looks like I forgot to get a grid to print out on this, but I think I can do it well enough. And so then this is PA XA right here. Now, if we wanted YA, let's just pull this off to us. We know that YA is going to equal to PA divided by P. So if we wanted that, we know that the total system pressure is 2 atmospheres. And so that means that just YA is equal to 0.1. Now, say we wanted CAL. Well, CAL is going to equal to XA multiplied by CL. Okay, but remember that CL is approximated by the density of the solvent divided by the molecular weight of the solvent. For in this case here, we should probably label this. A is CH3, and B would be H2O, and C would be air. Then in that case, this would be 1,000 kilogram per meter cube. That's the density of liquid water. Let's indicate that this is the solvent here. And that's going to equal to 55.6 kg mole per meter cubed. So then if we wanted to get CAL, then we could just multiply that through. And that'll be 2.5 kg mole per meter cubed. So see, we can do this CEHE 333 style of interconversion to get to any units of concentration that we want. Now, part B, it asks, what are the interface compositions XAI and PAI and XA and PA star? And then we want to XA star and PA star. Somehow the little XA star didn't get on the problem statement, but I'll indicate it correctly here. All right. What time do we have? First off, let's just get PA star and XA star because they're the easiest to do. So let's go to the figure here. All right. And I'm just going to use a little ruler here to just make a dotted line to extend that all the way across and all the way down. Okay, so when we do that, go across here all the way. Hopefully everyone can see those dotted lines. All right. When we just draw it in like this, then there's going to be two locales where the intersection occurs. And we know from this one right here, this is going to be PA star because it's that composition in equilibrium with XA. And then we know over here, all right, that this is going to be XA star because it's that composition in equilibrium with PA. So then when we look at those, we can write down their numerical values. All right, and we get XA star equal to about 0.12, and PA star given here of 0.06, thereabout. All right, now we need to think about PA and PAI. Let's see, how much time do I have here? Let's just do this real quick. Now, the reason why I chose this problem in this set of coordinate systems is because we haven't worked in this exact combination yet, but I want to show you the principle of how you can always get it to work out. You know that these two fluxes here have to be equivalent to one another. So that when we put this through, all right, we'll get a minus just by solving the two, or just by equating the two, I'm sorry. In this case here, the slope will be a minus kx on kg. So when we go to this diagram here, all right, the slope that'll get us those interface compositions is to be minus kx on little kg. So in terms of what we know from the coefficients, remember I couldn't write down everything up front, all right? But we know that KL is equal to 0.045 meters per second. And we know that kg is equal to, what we got here? 1.0 kg mole per meter squared second atmospheres. So somehow we've got to get kx. But if we recall, get that out of the way. Recall that Na is equal to a little kx xai minus xa, which is going to equal to the little kl cal minus cal. Sorry about that. CALI minus CAL. All right, then we know that little kx is going to equal to C sub L multiplied by K sub L. And we did that earlier up in part A. So then we can just put that through.
Can you move the paper a little bit to the right, please? Thank you.
And so then we can actually get the numerical value for kx. And notice here that the units changed. They're actually consistent now with flux because it's in a mole fraction driving force. So now we're almost done, but we're also out of time, okay? So the strategy, okay, will be to now know that we have kx and kg, is we can use those to get the slope here, and we already know PA and SA, and then from that, we will get PAI and XAI, and then once we have that, this non-linear equilibrium, okay, we will be able to get the overall coefficients. So that's what we're going to do at the top of class on tomorrow. We'll just briefly recap this last part. We'll do parts C, and then we'll move on and do another problem. That concludes today's class. Both today's lecture and the lecture on Friday were recorded, but I have not posted the recordings yet. And I'll let you know when I do. With that, I'll stick around another 10 minutes or so if you want to ask questions related to course content and concepts presented in today's lecture. And if not, have a great morning and a great afternoon. Thank you for coming.
Thank you.
I have a question.